Hi everyone, I'm glad to participate in this international conference and to share with you a part of my thesis work. So my name is Safa Jemai, our PhD student, and my presentation is entitled Crystal Growth and Design of Various Shapes of PbS, Micro and Nanocrystals from a Hydrothermal Process. So to begin, it's interesting to present my principal material during this study. It's the lead sulfide, which has an interesting properties. It has a face-centered cubic structure, a Let's parameter around 5.936 angstrom. It has a narrow bulk direct band gap of 0.41 electron volt at room temperature, which can be increased by simply decreasing the size. It has also a large excitant Bohr radius of 18 nanometer and exhibits strong quantum size effects when synthesized under the form of nanoparticles having an average size smaller than 18 nanometer. So because of its interesting properties, lead sulfide was used in many applications field, such as photocatalysis, gas sensors, and photovoltaic devices. So to board this presentation, four principal parts will take place. I will begin by objectives, then second part will talk about the optimization of PbS particles deposition. The third part will talk about the structural and morphological analysis and results, and finally conclusion and perspectives. So the aim of this work was the optimization of the deposition of PbS nanostructures in the shortest possible time, starting by microstructures by the hydrothermal method, while just acting on a few simple parameters. So the study revolves around three principal steps. The first step consists on the solution preparation by mixing the necessary precursors for the formation of PbS. Step 2 is the hydrothermal treatment in an oven at a fixed temperature of 150 degrees. And the final step is the study of the effect of varying synthesis parameters on the structural and morphological properties of PbS. So to study the effect of different parameters, synthesis parameters on the properties of PbS, four experimental series were carried out. So in series A, we varied the concentration from 0.5 molar until 0.05 molar. And the shape was dendrites. In series B, we increased the reaction time from 2 hours until 6 hours, and the shape results was monoarm dendrites. In series C, we keep all the experimental work, but we added a complexing agent, and we got octahedral crystals. And finally, in series D, we changed the anionic precursor while decreased the concentration from 0.5 molar until 0.025 molar, and we succeeded synthesizing quasi-spherical nanoparticles. So to study the structural and morphological properties of our samples, we used high-resolution FISM and high-resolution TEM for the morphology and Exergy for the structure. For the morphology properties of our samples, as we can see here, figure 1A presents the shape of our products in series A. So we succeeded synthesizing starfish-shaped PbS dendrites with 6 6 symmetric arms extending from the center. In each arm is composed from nanorods, which are parallel to each other. It's the result of decreasing the concentration of precursors from 0.5 molar until 0.1 molar. But when we decrease the concentration up to 0.05 molar, a mixture of curious irregular shaped PbS dendrites crystals takes place. And here, a careful observation of the PbS crystal view shows that each facet of the PbS structures has nanoscale spherical particles with an average diameter of 12 nanometer. So in Series B, while increasing the reaction time from 2 hours until 6 hours, we can't see a complete starfish-shaped dendrite PbS, but all the starfish-shaped structure split into single-arm PbS dendrites. In Series D, once we added a complex zinc agent, this leads to the formation of octahedral crystals and lots of sheet-like crystals. This is due to the formation of a complex due to the reaction between the complex zinc agent with the Pb2, which blocks the formation of starfish PbS dendrites. And finally, in Series D, a simple act on upon changing the anionic precursor and a simple act on the anionic precursor concentration, this is a lead to the change of the structure of PbS particles from dendrites to quasi-spherical nanoparticles. Here, as we can see, for the chemical analysis by EDX, this revealed the presence of Pb and S elements without any impurities. And here the high resolution TEM image for quasi-spherical nanoparticles shows the interreticular distance d of approximately 0.294 nanometer, corresponding to the crystallographic orientation 100. So now we go through the Exergy analysis. The figure 3 present the Exergy patterns of PbS structures corresponding to the A, C, and D series, and the figure 3b compare the Exergy spectrum of quasi-spherical nanoparticles and their different concentration going from 0.5 molar until 0.025 molar. Here, as we can see, the samples are of a very good crystalline quality, and no impurities and no oxides are detected. As shown in the table, we deduced the fall width at half maximum and the average crystalline size by referring to the 1-1-1 orientation. So when we increase the concentration of precursors from 0.1 to 0.5 molar, it means by factor of 5, the average PbS crystalline size increased from 28.2 to 34 nanometer, so 5.8 nanometer. And when increasing the concentration of precursors by factor of 4, it means from 0.025 molar until 0.1 molar, the average PbS crystalline size increased just by 0.2 nanometer. Here one can conclude that by just acting on the concentration of precursor, we can tune the average PbS crystalline size. So, as perspectives of our works, we investigate the experimental growth mechanism of PbS dendrites by the variation of the reaction temperature. As application, we will try to study the photocatalytic performance of PbS dendrites, special because of its special geometric configuration and higher charge transfer due to their branched nature. And finally, we will try to associate the PbS nanoparticles with titanium dioxide nanotubes, seeing that titanium dioxide is considered as a wide gap semiconductor. And we will try to study the influence of decorating titanium dioxide nanotubes by PbS nanoparticles on the optical properties and absorbance of titanium dioxide nanotubes, and also try to study the photocatalytic performance of photoanodes, PbS nanoparticles, titanium dioxide nanotubes. So to conclude, the PbS micro nanocrystals with different shape were synthesized by facilitated hydrothermal route by acting on deposition parameters. High resolution FISM and high resolution TEM show the dependence of deposited PbS structure on the experimental parameters. And finally, the Exergy spectrum confirms the formation of different PbS structure without any impurities. Thank you for your attention, and for more details, you can just check my publication in Materials Characterization Journal. Thank you.